Welcome to our tutor time on our web page or on my web page. So we're starting a new unit today. Today was November the 28th. What you missed in class is what we're going to go over. So our unit is Unit 6, Momentum and Collisions, and you should write this on page 67. Page 68 will be here or in your hanging file folder, and page 69 is going to be where you should be taking your notes. So when we talk about momentum, we often talk about it as a normal life term. And so what we're used to hearing for the word momentum is like a sports commentator saying, okay, the Dallas Cowboys have the momentum of the game right now, which typically is inferring that they are winning or they are up in points. But physics has a specific definition for that, and momentum is actually a physics term. Momentum is actually represented by the letter P, and it is the quantity of motion that an object has, or it is the product of an object's mass and velocity. The units that we use to write after momentum is the kilogram meters per second. For short, we write big N, little s. Now, I want to recall right here that the Newton is actually kilograms meters per second squared. So NS is different from N. And the reason is that it's the square on the seconds. But going back to momentum, the momentum formula is P equals mass times the change of velocity. So basically, momentum is how difficult it is to change what an object is doing. So you will have to watch this video um, on where it says PowerPoints, but we're going to scroll on through it for now. So an object's momentum will change if its mass and or velocity changes. So remember that a change in velocity can be either a change in speed or direction, and it is called acceleration. So velocity is a vector, which means it has magnitude and direction, okay? Acceleration, remember, is calculated by taking your final velocity minus your initial velocity and dividing it by t. Now, remembering this formula or recalling this formula is important for a couple of slides later. So, the more mass that an object has, the more momentum it has. So, if it has a higher velocity, the higher the momentum, because there is a direct relationship between the momentum and the mass, and a direct relationship or directly proportional relationship between the momentum and the velocity. So let's think about football for a moment. What is the size of the linebacker compared to that of the running back or the guy who throws the ball, the quarterback? They're bigger because they are going to tackle the other people. And so we want them to have a greater momentum so that they can protect the person who has the ball. So when you are looking out there and trying to figure out who it is that your opponent is, you see the biggest guy, you may wince a little bit. So, but just because he's the biggest guy doesn't mean that necessarily he has the biggest momentum of all the guys there, because remember, you've got to account for the velocity as well. And some football players with a big mass have a small velocity. Some with a big mass have a fast velocity, and that's an awesome football player right there. So here, when Isaac Newton was starting to introduce the idea of how objects move, he actually went at an angle or an approach of talking about an impulse. Now, when I think of the word impulse, I think of actually the nervous impulses. And so you have to get a stimulus in order to get an impulse in order for their reaction to occur. So I'm sure that that may be the origin of this term. But typically, when we think about movement, I don't think of the word impulse, but an impulse is nothing more than a force that is acting on an object. But this force that's acting on an object happens at an interval of time. We use the letter J to represent impulse, and its unit is going to be ns as well. So to calculate impulse, J equals the force times the time interval. Now, we're getting to our impulse momentum theory or theorem. So according to Newton's law, remember that a net force causes an object to accelerate or change its velocity. Now, when we did our free body diagrams, sometimes we were given the net force, or we could calculate the net force because we were given the force of the object, or the force that was being put on the object, and the object's moving in that direction, and then the, the friction force going the opposite, and we were able to just do simple subtraction. But if we're not given that, there's a different way to calculate the net force. And so hopefully you remember the formula for net force. I'll give you a minute to think about it. Is mass times acceleration. Now we just talked about acceleration being written as this, okay? And we know that impulse is F times t. And we know that momentum is the mass times the change in velocity. So what I'm going at with this, the reason why I'm bringing these back up is because these formulas are the ones that are going to help us understand how we get this formula. So remember that a force acting on a ball for a time increases its momentum, its mv, okay, because we talked about that earlier. Now, if I have the force and I have m, I can actually put Vf minus Vi divided by t, and that is very appropriate because that is the same thing as A, right? So how do I get this impulse equals momentum? So I take my t and I divide both sides of it, and when I do that, this is the formula I get. And this formula is very handy because what it is telling us is that the impulse is the same as the momentum. So whatever I calculate for the impulse, if I'm given my force and my time in a problem, a word problem, that's also going to be my momentum, or vice versa. You'll have to excuse the noise. I'm recording, and then there's some people in the classroom as well making things up. So this video, you'll have to go to the web page where it says PowerPoints to get that, to watch it. So after you've watched that video, it's usually better for you to watch the video before you start this. But to minimize the effect of the force on an object involved in a collision, the time must be increased. To maximize the effect of the force on an object involved in a collision, the time must be decreased. But the change in the momentum is the same either way. So you can think of it as the bigger the force or the smaller the time, the bigger the force, and that's a bad situation, okay? So if you threw an egg at a wall, what would the egg do? It's going to crack open. But if you have a small force, well, now actually, if you have a longer amount of time that the object, before it collides into another object, your force is smaller. That's a better situation. Typically, an egg hits a sheet, that's an example, and that egg does not bust. So if you watched that video a moment ago prior to this slide, this will make a lot of sense to you. But you do need to make sure that you have this information. So here's our first example. It says the face of a hockey stick exerts an average force of 4,000 newtons for 0.002 seconds. What is the impulse imparted on the puck? Well, we're being asked to find the impulse. So what is the formula? J equals force times T. So I paused there so that you could write that down or think of it yourself. Make sure that you're taking notes as you're watching these videos because that is an expectation when I grade your journals. So 4,000 times 0.002 is 8 ns. Okay? And there is our example 1. Example 2, it says Cara, Cara, Cara Les was applying her makeup when she drove into a busy school parking lot this morning, unaware that Lisa Ford was stopped in her way 30 feet ahead. Cara rear-ended Lisa's rented Taurus. Cara's 1,300 kilogram car was moving at 11 meters per second and stopped in 0.14 seconds. A is asking us to determine the momentum change of Cara's car. Well, momentum is P and it is calculated taking the mass times the acceleration. So if I have the mass of 1,300 kilograms, then I have the acceleration of 11 meters. I end up with 14,300 ns. Now remember the slide before, momentum and impulse are equal because this is ft and this is m times, oops, not a, velocity, or the change of it. Okay, so that means that to determine the impulse experience by Cara's car, it's 14,300 ns as well. But if we want to determine the magnitude of the force, that means I have to find F. Remember the formula is this. Okay, so I want to find this. I have that because it's here and here. My time was given to me. I just have to get t on the other side of the equation and F by itself. So I divide both sides by t. So I take 14,300 ns and I divide it by 0.14 s. And the answer that you should come up with is, it's a big answer actually, and it's going to be newtons. Not ns, but newtons, because remember we're doing force and there's an s on the bottom. Okay, remember you can pause this video anytime you need to. Example 3, I have a 50-gram golf ball that leaves the face of the club at 20 meters per second. I want to know what the momentum is of the golf ball. Well, the momentum, remember, is P equals M times V, but M has to be in kilograms. They gave us 50 grams. Well, 1 kilogram is equivalent to 1,000 grams. So that means I'm going to move this decimal 3 times because I have 3 zeros, so I've got a 0.05 kilograms here. So I take 0.05 kilograms times my 20 meters per second, and what I get is a 1. You may have already done that. NS. And then it says if the club is in contact for 0.002 seconds, I want to know what my force is. Well, remember my force is my mv divided by t, because remember this. Okay, we just move this to the other side by dividing it. That's how we got this. Okay, so if I put my mv, which I have up here, 1, and I divided it by 0.002 seconds, you get 500 newtons. That is the answer for that one. So here's another slide that we need to take notes on. Velocity and force are vectors. They have magnitude and direction. Therefore, momentum and impulse are vectors as well because they have magnitude and direction. There are two things that can change with vectors, the magnitude or the direction. So you're going to treat these next problems the same way, but you need to include negatives to indicate that the object is now traveling the opposite way. So what are we doing different? We have two things that can change, all right? We have magnitude and direction that's changing. So example 4, we have a 500-gram baseball. Well, what do we need to do with that grams? We need to convert it to kilograms. 1,000 grams equals 1 kilogram. That's how we do it. I didn't show you that little trick earlier, but that's how you do it. So that's 0.5 kilograms. So we're going to get, we have to get, in order to get to our force, remember, we've got to find our momentum. So we have our mass, which is 0.5 times what is 20 meters per second. Now, 20 meters per second is my VF or VI. Well, let's read the problem. The bat is going 20 meters per second, then it strikes, and then the ball is going 20 meters per second, then it strikes a bat. The bat is in contact with a ball for 0.02 seconds, and then it leaves the opposite direction at a 40 meters per second. So what is the average force on the ball? So we're changing direction. So that means that if you think about displacement, it's going this way and now it's going back that way. What do we always do? Well, we subtract, okay? So our F final is 40 minus, okay, and that's a minus, our initial, which is 20. So we end up adding those together and we get 60 meters per second times our 0.5 kilogram divided by our time, which is 0.002. And your answer is this. That's the force. Whew, that's a big force. Okay. And that is the end of our video. Thanks for watching. Bye.